Hello, everybody. My name is Mark Chupka. I'm the Vice President for Research and Programs here at the Energy Storage Association. Thank you for attending today's webinar on overcoming storage interconnection barriers. This webinar is being recorded. Everyone who registered will also receive a link to the recording and slides within the next couple of days. Questions can be submitted at any time throughout the webinar via the questions chat box in your browser. And we'll get to those after our speakers finish their presentation. In the text of your question, please indicate to whom you would like your question addressed. All meetings and teleconferences of the Energy Storage Association are held in accordance with our antitrust guidelines. We ask that you abide by these guidelines during today's webinar. The full guidelines are available in the members area of the ESA website. If you are not yet an ESA member and would like some more information, you can reach out to my colleague, Brenda Lovell. Membership includes free access to all of our webinars, including many that are exclusively for members, among numerous other benefits. So please contact Brenda for more information. Before we begin, I'd like to announce a related upcoming ESA event. ESA will host an in-depth seminar on planning and energy storage on December 2nd and 3rd. Please check our website for additional information. And with that, I will turn it over to Radina.
Thank you so much, Mark, and thank you everyone for joining us today. We really appreciate having you with us in this webinar, and we look forward to the presentation and hearing from you as well on the issue of energy storage interconnection. My name is Radina Valova. I am Regulatory Vice President with the Interstate Renewable Energy Council, and with me today are my colleagues Mari Hernandez, Assistant Director of the Regulatory Program, and Brian Leidick, Chief Regulatory Engineer for IREC. Next slide, please. Thank you so much. A little bit about the Interstate Renewable Energy Council before we jump into the substance. IREC works toward building the foundation for the rapid adoption of clean energy and energy efficiency in order to benefit people, the economy, and our planet. And our driving vision is achieving a 100% clean energy future that is reliable, resilient, and equitable. Next slide. And we would like to thank the Department of Energy's Solar Energy Technologies Office for supporting this project. A little bit about the project partners. So first of all, the project that we are here to discuss today, supported by the Department of Energy, is building a technically reliable interconnection evolution for storage, or batteries. And this is a 3-year project that is being administered by IREC in partnership with the Energy Storage Association and our other partners that are members of the Storage Interconnection Committee that you see here. And as you can see, this is a diverse group of partners ranging from storage developers, the solar industry, utilities, and also Sheet Macaulay Weinberger, which represents IREC, and including as part of this project. And I want to say a special thank you to our project partners, particularly the Energy Storage Association, who is a key technical advisor on this project, as well as the Electric Power Research Institute, the California Solar and Storage Association, the New Hampshire Electric Cooperative, Pacific Core, the Solar Energy Industries Association, and SMW. But we're not working alone. A key part of the project is connecting with stakeholders from across the country to get your valuable insights on the challenges and solutions related to storage and solar plus storage interconnection, and that is why we're here today. So the agenda for today is an overview of the project itself, And then we will jump into identifying the list of issues that we have thus far marked as the list of storage and solar plus storage interconnection issues that we have thus far identified and marked as being significant and requiring solutions in order to reduce barriers to storage deployment. And throughout the process, we will have a series of polls to solicit your feedback and your thoughts on how important or how priority level each issue is. And we will end with questions and answers. All right, so a little bit about the project itself. BATRIES, as I mentioned, is a 3-year project, and the objective is to simplify the interconnection process for both standalone energy storage and solar plus storage by identifying and developing solutions to both regulatory and technical barriers. And ultimately, the goal is to reduce soft costs related to interconnection and enable more storage and solar plus storage integration. And our focus is on behind the meter projects that connect to the distribution grid. The ultimate outcome of the project will be a toolkit of solutions that will apply to diverse states and markets. Our goal is to have solutions that states that are still in the initial stages of growing their solar markets can apply in order to avoid some of the pitfalls that come with not having the necessary interconnection procedures in place in order to avoid undue delays and costs once the market does develop, as well as states that already have more advanced storage markets where we want to address some of the issues that may arise as a result of the growth in deployment that existing interconnection rules might not resolve. And the timeline for the project is occurring through 3 key stages. With the first stage, in which we are currently operating, involves developing a roadmap. And this roadmap is going to spell out the initial list of storage and solar plus storage interconnection issues that we have identified, as well as the initial set of solutions that the project will work towards developing to address those challenges. And as part of developing the roadmap, one of our primary activities, as I mentioned earlier, is to host rounds of stakeholder engagement in order to receive very valuable feedback from people actually practicing in the field who are seeing these issues play out on the ground. And stage 2 of the project is developing the toolkit itself. And in terms of the types of solutions that the toolkit may include, it could range from checklists, templates, case studies, or featured projects that can then be used to guide and inform the development of interconnection rules and procedures. And last but not least, in phase 3, we will conduct an intensive outreach and education process to ensure that the toolkit is reaching the people who are working on these complex storage interconnection issues, including regulators, utilities, and developers. And in terms of where we are now, the Storage Interconnection Council, our group of partners, has identified an initial set of storage and solar plus storage interconnection challenges that we feel it may be appropriate for the project to address, and which we'll walk through in just a moment. So I'm going to turn it over now to my colleague, Mari Hernandez, who can speak a little bit to how we selected those issues, meaning the decision-making criteria we used in developing the set of issues, as well as the 3 bar categories into which the issues fall. Mari, take it away.
Great. Thanks so much, Radina. And thank you all for joining. As Radina said, this is a really important part of this process. And so we do hope that you'll bring your questions and definitely provide your input on the project. So as Rodina was saying, our first task was really to determine the scope of the project and come up with that set of storage interconnection challenges that we want to address. So the project really officially kicked off over the summer, and our first several meetings were dedicated to that, gathering input from all project partners on their highest priority issues. So what we got from that process was a list of nearly 40 challenges, which was way more than we could tackle within the project. So our next step was to consolidate and refine that list to a more manageable set of issues, that we could actually tackle within the 3-year project. So to help with that, we created a set of evaluation criteria that we could apply to the issues, and that included, this isn't exhaustive, but it included whether the issue or the solution was something that would have a measurable impact on the storage interconnection process. And we don't have an idea of all of the solutions, and that's where stakeholder input comes in, but just kind of gauging from our, immediate knowledge without any further research, could it have a measurable impact? Was it specific to storage? Was it something that could apply to diverse states and markets? Was it something we could complete within the project timeframe? And was it already being worked on by other groups? So those were a few of the, evaluation criteria that we used, and we ended up narrowing the list down to about 16 challenges and subtopics. And that's what we're going to be going through today. What you see now are the broad buckets under which we put those challenges. So as you'll notice, if you look through all 3, there are, these are definitely interrelated and they have a lot of overlap. But this was just one way to categorize them and try to parse them out somewhat. So you'll see each of these, overarching issues again as we go through the underlying challenges and subtopics in the next few slides. If you could go to the next slide, please. So looking at the first overarching issue, we identified lack of grid transparency as a challenge that leads to greater inefficiency in the interconnection process. We've seen that providing more data on grid conditions up front can help developers design projects that avoid more costly study processes, help them site projects in more favorable locations, and reduce the number of speculative projects submitted for utility review. So what you see in the subtopics is one way to increase grid transparency through the use of hosting capacity analysis and maps, which can provide grid data to help with project siting before an application is submitted. And we're going to go through these somewhat quickly just because of time, and we want to leave time for questions. Again, just a reminder to submit questions through the chat box. But so moving on to the second challenge there, B, we know that energy storage systems add flexibility to a project that can help it mitigate the need for upgrades in the interconnection review process, but that process is typically not designed to allow for design changes to a project without requiring a full restudy. So addressing this could help to remedy this inefficiency within the process. So now we're going to run through or run a quick poll to see which of these issues you find to be most critical to streamlining the storage interconnection. We're going to do this with each section just to kind of gauge what your thoughts are on, how high priority these issues are within these topics. So if we could go ahead and launch, oh, there it is. So if you'll just take a couple seconds here to respond to this poll. And then I just reminded you to submit questions via the chat box. And Brian, I don't know if there's anything in there that we need to address right now because I'm not seeing the questions, but if there's anything we want to address, we could now and then move on to the next section.
No questions coming in yet. So I actually just got a couple here. Someone asked why focus only on behind the meter, and actually, we haven't. I don't know if anything was stated incorrectly there, but it's not necessarily just behind the meter storage, but anything on the distribution system. So we're not focusing on larger things that might be connected to transmission, but anything that could be just connected on the distribution system that could include non-behind the meter systems as well. There was one more question that asks or mentioned that it would be good to distinguish what is a general interconnection issue versus specific to storage. Meaning, and that is something I think, came up as we were trying to build this list of issues. There's lots of interconnection issues. The questioner says, just taking too long in the process or something like that, versus lack of clarity on rules specific to storage. And that's one thing that we really had to wade through and tried to decide and are trying to decide through this process, to focus on the really storage specific issues, or at least those issues that impact storage greatly. So some of these issues may not be fully, solely focused on storage. They could have impact on say a storage only or a solar only system. But we are trying to drill down onto those issues that are mostly storage focused. Thanks for those questions.
Yeah, and I would say, the reason we're doing these polls is to help prioritize within them. So, to the extent that you feel that there are some that are really storage specific that need to be addressed before some of these others that are less storage specific, please make your voice heard on these polls, because that's really going to help us as we continue to narrow our scope, because we're still trying to figure out, how much can we reasonably accomplish within a 3-year time period. And really, it's even more condensed than that, because part of that, as you saw, is about doing the outreach for the 3rd year. So we have really, this year we're trying to really focus in on what we're going to study and provide solutions on. So, and then one other thing I'll mention is we are going to put up our email addresses in a little bit, so you'll be able to reach out to us with any other questions or input you might have. And we're definitely open to that. So please take note of that in the screen at the end. And then I'm going to turn it over to you, Brian, so you can go through the next set of interconnection challenges. And we can close the poll now.
All right. Okay. Thank you, Mari. So yeah, the next. Yeah, here we go. So yeah, the next overall bucket of challenges that we've looked at is the lack of standardized verification processes for storage system behaviors. And really, storage systems are very flexible systems, a little bit different from, say, solar PV, which has a little bit more predictable output based on irradiance. And you're not generally changing the behavior of that output all that often, whereas storage, really you can tailor it to your use case and tailor the output as well, the discharging as well as the charging. That behavior isn't necessarily well standardized, and so verifying how a system will behave, at least the belief, from our team at the moment, is that it's a little more challenging for utility engineers who are trying to get these things through the interconnection process to, verify what a specific behavior would be dependent on the use case of the storage or dependent on other factors. So the kind of individual things that we've identified here, first off, the overall challenge is, can we standardize or how do we standardize in the verification of those capabilities and storage impacts? First one being defining and verifying the export and import controls. So storage systems, like I said, they are flexible. They can change their output level. And through the interconnection process or for other reasons, you might find a need to limit the output level or the export level across the point of common coupling, say, into the distribution system. That would be one way to maybe limit impacts on the distribution grid, even if your system, either storage system or storage plus solar system, could output more power, you might decide to limit that, as well as you may decide to limit the import values for charging purposes. And that can be done, generally, typically through control systems. There is this developing power controls system idea that there are test procedures being developed at UL for, and that is, that is focused on export and import limitations. Part of the impetus for that was for NEM compliance, where if you have an NEM generator, say a solar system plus a storage system, especially if they are AC coupled, there's a desire to standardize the verification that that storage system won't be taking in energy from the distribution system and then exporting it back out again and claiming NEM credits. So that's one potential use case for doing this. But there are other, as I mentioned, reasons for defining those export and import controls. And then number 2, identifying the impacts of storage system power transitions. This is, once again, just kind of points to that flexibility of storage where you can go from, say, full output to, or full discharge to full charge mode, and dependent on the equipment, the manufacturer, and the topology, you can do that very, very, very quickly. You can implement ramp rates. Those ramp rates might be somewhat dependent on the manufacturer implementations or customer parameters that have been input. But a lot of that is not well standardized as well. So, and then that relates to later on how the utility would actually evaluate those impacts to the distribution system. And right now they're probably, scouring through spec sheets and sometimes maybe even contacting manufacturers to get the data that they need. So once again, it may be useful to have more standardized ways of verifying how storage systems go through power transitions from one level of output power to another. And it's really not just from charge to discharge, but even potentially what are the ramp rates between 2 levels of output power, since they can potentially do that very quickly. And then third, identifying flicker or rapid voltage change risks. That somewhat relates to number 2 here. Anytime you do change output power levels very drastically and quickly, there's the potential for introducing flicker or rapid voltage changes. However, those the evaluation of those isn't completely well understood, either on an individual inverter basis or individual storage system basis, or in aggregate, especially when we start thinking about how storage systems may be introducing use cases that depend on a common signal. And if there are many storage systems on a distribution circuit, say, that are using a common signal and reacting in a similar manner, how does that affect flicker or rapid voltage changes? And then number 4 is incorporating updated codes and standards. Really, there are standards in place already or developed or being developed that we, feel probably needed to be included in interconnection rules. One big one being the updated IEEE 1547/2018 standard, which includes some storage-specific requirements, but is an interconnection standard in general. And then beyond that, UL is developing some, there's the NEC. So just really, since the interconnection rules haven't fully caught up to the standards revisions and that there are more being developed, we want to review which ones and how should they be implemented in the interconnection rules. So why don't we go ahead and bring up the poll here. So once again, we'd like you to basically tell us, out of those 4 in this bucket, which one do you feel is the most critical to streamlining storage interconnection as you see it? And as we do this, once again, I'll just note the selections here: defining and verifying export and import controls, identifying the impacts of the energy storage system power transitions, identifying flicker or rapid voltage change risks, and incorporating the updated codes and standards. So, some of these are rather detailed, some of them are a little more broad, but just want to get your idea on what issues do you think you're seeing or could potentially see in the interconnection process? Now, let's see, I think we've got a couple questions here could potentially dive into while we're waiting on this.
Hey, Brian.
Mm-hmm.
I just forgot to mention too that these issues as we're going through them are not in any kind of order of importance on our end. So I didn't want people to think that we've already ordered them in terms of importance, and kind of wish they could be randomly placed in these polls, because that, just so you can see them and not feel like they're already in some sort of ranked order.
We've got a couple questions here. Maybe we'll come back to at the end because they relate to the last category that we were chatting about in terms of the hosting capacity analysis. There was one question about how does degradation over time factor into the battery strategy of cycle life versus calendar life. Excuse me. It's not something we'd previously looked at, and it sounds to me maybe a little bit more of a technical question that we're really focused on. What are the interconnection rule impacts when you're going through the interconnection process? So there might be something there. I'm curious as to whether the questioner maybe thinks there is something there in terms of evaluating the effectiveness of a storage or battery system over life, maybe versus the use case, and whether there could be impacts from, say, how the utility requires that interconnection. I'm not certain that the questioner is attempting to make that connection, but it does bring up something that we hadn't raised before. But I think that deserves some discussion. I think we've had somewhat similar discussions in terms of inverter-based systems and the smart inverter realm in terms of the wear and tear of utilizing VARs for distribution system needs and whatnot. It may be potentially beyond our interconnection project here, but we'll definitely take that under advisement. I'm not certain if we know how many responses we've gotten, but we might be able to wrap it up here in just a few minutes. So if you haven't voted, please do get your selections in here. I did get one more question about the excluding transmission level energy storage. Really, just because we are focused on the impacts at the distribution system level, and we're working with distribution utilities, it might be potentially a different type of project if we were looking at transmission level interconnection, which go through slightly different processes. So thank you for the question. I think the way that our project is defined and the project partners that we've got, we've really honed in on those distribution system and mostly radial type of circuits, although we do have, in our next section, we'll talk a little bit about networks, but we are focused on distribution system issues. So why don't we wrap up this poll here? And let's see. So the import and export controls was winning, followed by codes and standards, impacts of power transition, and then flicker and rapid voltage change, which is a somewhat esoteric concept. So thank you, everybody. I think I'll be handing it off to Radina now to go over our next category of items.
Great. Thank you so much, Brian. And thank you, everyone, for participating in the polls. Your feedback through the polls is quite important for us because, as Maury mentioned, we started with a list of nearly 40 storage interconnection issues. We've boiled it down to the issues you're seeing now, but we still need to make sure that as we move on to drafting the toolkit, we really are addressing the storage interconnection barriers that are the most critical. And so we very much value your input through the polling process and your questions and comments. All right, so we're moving now to the third overarching issue that we have identified, which is the lack of clarity within the rules related to evaluating storage. In the previous section, Brian covered the very technical and engineering design issues related to storage. Now we're turning to the regulatory side. The interconnection rules and regulations we need to consider in order to minimize barriers to storage and solar plus storage interconnection, which of course would work in tandem with any recommendations we develop around the technology and engineering related processes. All right, so just going down the list here. First and foremost is the general question of how do interconnection rules need to be updated in order to be inclusive of energy storage. Storage, as we've already discussed, has very different capabilities compared to other types of distributed energy resources. And interconnection rules have to include specific provisions to target the operating capabilities of storage in a way that allows distribution system operators to ensure reliability, but that also minimizes the time and expense of the interconnection process. So there are a couple of desired outcomes in the interconnection rules and regulations development process. And the rules process can include, at a very basic level, having storage be included in the definition of generating facilities, and just more concretely defining very explicitly storage as an applicable resource under the interconnection rules, as well as a number of other factors, which we'll go into a little bit more detail now. So I'm going to hand it back to you, Brian, for issue B, how to evaluate flexible loads and resources.
Okay, thank you. So once again, that flexibility of storage comes into play here, and we think it's possible for that flexibility to play a role in how the utility evaluates the distribution system impacts, hopefully to mitigate those impacts potentially, as well as potentially utilizing storage for certain use cases. So one of the first ones we have listed here is defining the rules for fixed schedule DER operation, basically meaning that before we have a communication system built out, especially for smaller systems that are widely dispersed and might require something like a DERMS system, we'd be thinking about how can these systems autonomously change their output levels in order to meet distribution systems needs, basically. And so they could be utilizing, going back to that import and export control concept, they might be using controllers to manage their import or export over time on a schedule in order to respond to how, say, load changes and how thermal constraints, say, change over time throughout the year on a distribution system circuit. There's not necessarily a great idea at the moment how granular we can get there. There could potentially be some interplay with hosting capacity analyses to say, well, we know load fluctuates like this on this circuit, and we can say that by season or perhaps by month, a certain hosting capacity value could be given, and energy storage could more closely tailor its output level to that hosting capacity value. That's one potential use case for that. So really, defining those rules. Once again, this probably ties back to standards as well, about how could a storage system operate autonomously on a fixed schedule without that utility intervention of a control signal being sent to it. That leads into number two, then defining those rules for DER responses to dynamic signals, where you could have a communication system with a signal being sent, say, from the utility or through an aggregator, and how those systems can respond to constraints on the distribution system or for different use cases. And then third, somewhat ties into potentially both of these, is defining the telemetry and metering requirements by the use case. And we're really, mostly focused typically on, kilowatt hour type metering here, which seems to be a big area, well, a potential area at least of contention when it comes to energy storage systems, and especially maybe when we talk about net energy metering coupled systems, energy storage systems, solar plus storage, say, where the different types of meter configurations could be, numerous, depending on, what information you want to get, depending on whether you have an AC coupled or a DC coupled system. Do you have to do DC metering? And some of this potentially also relates back to the net energy metering integrity issues. But in general, there's going to be use cases that require telemetry and metering. The utilities may be interested in terms of their planning and operations, what they need in order to know what the storage system is doing and what type of metering needs to be applied there. So I think that's it for B. Let's go back to you, Radina.
Thank you so much, Brian. And so for inadvertent export, this
Hey, Radina.
Yeah.
We do have a poll if we'd like to use it on the subtopics here.
Yes, good point. Thank you so much. All right, let's get to that. Thanks, Mari, and sorry for jumping ahead there.
Yeah, thanks for reminding us. Yeah, so those, based on those three, just for that one sub-item in B there, which of these would you see as most critical in terms of evaluating the flexible loads and resources, whether defining the rules for a fixed schedule for DER operation, defining the rules under which the DERs can respond to dynamic signals from utilities or aggregators, and defining use cases that require specific telemetry or metering requirements by use case. We had one more question, which was kind of an overall question about the scope of the project, questioning about systems connected to the distribution grid, but providing ancillary services to RTOs or ISOs. And that, definitely could or would be a part of the project. We haven't, I don't think, spelled out anything specific about that interaction, but it's certainly one of the types of interactions that we were envisioning here. Potentially even here under number 2, defining the rules for response to dynamic signals, but also in the previous section when we talked about standardizing the verification processes for storage system behaviors, where you could have aggregate effects of power system changes from many different energy storage systems. That is certainly something that is within the scope. So thanks for asking that.
All right, and thank you everyone for voting. It looks like we've got a pretty good voter turnout here. Let's give it just one more minute and see if we can get a few more responses. And one thing we haven't touched on, this is Radina. One thing we haven't really touched on thus far is sharing a little bit more about the type of stakeholder outreach that we're doing as part of this phase of the project. Again, we're in this first phase where we are developing the roadmap that will enable us to prepare and draft the toolkit of solutions to storage interconnection barriers. And so we're very appreciative to the Energy Storage Association for hosting this webinar and allowing us to speak with you today. We are also reaching out to other stakeholder groups, whether it's from a solar perspective, from a utility perspective, and also from a regulator's perspective. So our aim is to get as diverse a set of viewpoints on these issues as possible. Let's see, do we want to give the poll another minute, or are we good to wrap up and move on?
I think we could probably wrap it up here if everybody give it a couple. Okay.
Wow.
Dynamic signal is winning out there. Interesting. Thank you for your thoughts there.
All right, let us move on to inadvertent export. Thank you so much. Oops, skipped ahead a little here. All right. So one of the biggest little in the sense of we're talking about a very small amount of export. So it's one of the biggest little challenges on this list is inadvertent export, which can occur when, for example, if a customer's system is sized too closely to match their load, or if a customer has a very large load, such as an electric vehicle, and that load ends up turning off while it is drawing from the battery, from the storage system. And when this happens, the battery system inadvertently exports small amounts of power for very short durations when these unanticipated load fluctuations occur. So there is some concern from the utility perspective about the potential reliability impacts this can have. And so a lot of existing interconnection rules either don't consider this issue at all, or if they do, they, and this is kind of also a theme under letter D here, how to evaluate non-exporting and limited export systems. If interconnection rules do consider the issue of inadvertent export, they can tend to take a worst case scenario approach and impose what can sometimes be very burdensome requirements, both in terms of time and cost of interconnection. And so one of the steps that regulators can take in addressing inadvertent export is to start by, first of all, including explicit definitions of what inadvertent export is and specific provisions for addressing it in their interconnection regulations. And we also need to clarify whether or not systems can or permitted under the rules to inadvertently export. Can these systems interconnect at all? And if so, under what conditions? And one of the challenges with rules that completely disallow inadvertent export is that this can serve as a barrier to storage deployment because it limits the amount of value that storage that a customer can get from the storage system. And so again, the amount of export we're talking about might be very small, but it is a big challenge from the regulatory perspective. And then moving on to the next issue related to this, but from a slightly different perspective, the question here is, how do we evaluate within the interconnection screening or study process energy storage systems that are completely non-exporting or that have very limited export? And so we really are driving towards a screening or study process that, as I mentioned in the beginning, addresses the reliability concerns of distribution system operators, but that is also cost and time efficient from the storage developer perspective, and doesn't, hopefully does not impact ultimately the financial benefits to the customer of owning and operating the storage system. So storage can export to the grid, but that doesn't mean that every system is designed to do so. Whether or not a particular storage system exports is going to depend on the desires of the customer, how the system is designed, and various other factors. But again, as with the import and export issue, very often the screening or study process assumes that export will occur or otherwise imposes unnecessary requirements, which can increase the cost and time of interconnection. So for systems that are non-exporting completely, screening really doesn't need, for example, to include any consideration or certainly not detailed consideration of the amount of electricity that the system exports to the grid. And another factor is whether or not there is a definition of what non-exporting means, and whether or not it means completely disallowing any level of export or recognizing that negligible amounts of inadvertent export can be managed without any serious impacts to the grid. And again, in both cases, we want to avoid an overly burdensome review process while addressing system reliability concerns. And Brian, I will hand it back to you for the last issue, how to interconnect storage to network systems.
Sure. So this one, somewhat of a niche issue, but network systems do occur in downtown environments. And if you're not very familiar with them, network systems are basically just different from the typical radial distribution feeder that we normally have, where a feeder can be connected in multiple locations, usually through different substations. So, a downtown area can have a very flexible and resilient electricity system, so that, if a fault occurs on a line, that fault can be isolated between 2 points very quickly, and very few customers could lose power rather than losing power all the way along a feeder. So it kind of allows for a type of reconfiguration on the fly, and it uses specialized equipment called network protectors in order to make that happen and ensure that power is not flowing in the wrong direction, which also make interconnecting a generator or DER to a network system much more challenging, because you cannot feed back much power onto the distribution network, because you could potentially risk flowing power in the wrong direction through a network protector and tripping it offline even when there is not a fault. So systems like that have to be reviewed rather carefully, or potentially limited in power output. Energy storage systems do have the potential, because of their flexibility in terms of managing export, to potentially make a difference in terms of connecting to network systems, energy storage systems by themselves, or when coupled, say, to a storage system, or to a solar system. So the idea would be to look at whether there actually is something there in order to allow for energy storage systems to do the power control that is necessary, potentially avoid overbuilding the system. A lot of times, if you are trying to attach a DER of any size to a network systems, you might be relying on very fast reacting relay type systems, or, as I said before, you might have to really undersize your system compared to the load of the customer in order to get it interconnected in an efficient manner. So really just trying to discover whether there are efficiencies there, or technical mitigations that can be offered by storage system being coupled at the network level. Really, does only apply to the downtown areas across the U.S. that do have network systems. So it's not the wide swath of the country, but still an important part of the load centers.
Great, thanks very much, Brian. And that really goes back to the desire for this project to address a wide range of jurisdictions across the US. So let's go on to our second to last poll here. So again, which of these issues that we just went over is most critical to streamlining storage and solar plus storage interconnection? And do we have any questions coming in on any of the challenges we just discussed?
I'm not seeing anything specifically on this section here. We do have a couple more scope questions, which we can answer while we're going through this poll. One of the questions is, does the scope address remote rural circuits or urban suburban dense load circuits? And kind of does relate to that, the last item I was mentioning about network systems in urban areas. But yeah, the scope applies to all those, anything on distribution. And so that, yeah, that would be rural as well as urban. We haven't identified any specific issues other than that networked system, you know, for downtown areas. But we haven't identified other issues that would necessarily change between an urban and rural environment. Although, you know, there are certainly, I would say, something like a voltage issue that, you know, is usually handled differently on those different types of circuits. I think it's a good question to raise and be aware of during the project, that we can, you know, potentially parse out some of these questions and issues dependent on the feeder characteristics, basically. So thank you for that. Another scope question for distribution circuits: what's the highest voltage level that our scope addresses? We have not, I don't believe, Mario Rodino, correct me if I'm wrong, I don't think we've really tried to close that to any specific voltage level. We're really just defining it as distribution systems, which would go through a distribution interconnection process. So, you know, I'd say that's typically, you know, up to 35 kV max. But yeah, I think it's just however it would be defined by the distribution utility.
Really great scope questions. And by the way, even though these questions don't necessarily relate to the issues themselves, they certainly are very helpful for us in making sure that when we describe the project in the toolkit, we are being very clear about the parameters. So thank you for those questions, very helpful. And
one
how
more
are we
are.
Oh, go ahead.
Yeah. When do we expect the toolkit to be finished, and will that be publicly available? Do you want to address that, Rodino?
Sure, yes. So this is, as I mentioned, a 3-year project. So we've got a ways to go before the toolkit is complete. We expect it to be completed in March of 2022. And yes, absolutely, it will be publicly available. We are designing first a specialized website that is going to present the toolkit. So it's going to be a one-stop shop where you can go and have hopefully an interactive way of viewing the solutions that the toolkit ultimately develops. And we will also most certainly be hosting a series of roundtables and webinars and otherwise making sure it gets out there. And if you are interested in hearing about updates on the project for when the toolkit is released, we will share, as Mari mentioned at the end, our email addresses. So feel free to email me, Mari, or Brian, and we're happy to get you on our email update list for this project.
Maybe we should close out this poll in the next 10 seconds here. let people get in. So we can just address a couple more questions before the end here.
Wow, it looks like we have a pretty close winner here as well.
We do have one last poll, and unfortunately, it was too many answers to include under GoToWeb. So, at the top here, you can see it's pollev.com/IREC. And I'm going to activate this. So once you go there, it will show your responses in real time. But this is actually a list of all of the issues we just went through, except for those specific sub issues that we went through in that last section. But everything else is listed here. So just kind of to get your idea, get an idea of what you think is the highest priority out of these, main topics. So if you all can do that, and then there's also an option to text if you don't want to go to that site, and you can pick from these letters here. That's weird, one of the bars went away. That's interesting.
As those results are coming in, since we just have a couple of minutes left here, why don't I try to address a couple more questions here. One of them was came up just a little after we had dropped off of the first overall issues we had, which was the inefficient and costly interconnection processes, and I think relates mostly to our how to improve grid transparency question. The question is, as it relates to hosting capacity analysis, various utilities have information, but what is the best way to harvest and use that information, and what parameters in the HCA are most important? I think those are the types of questions we would be hoping to answer as part of this this project in relation to how it helps streamline the interconnection of energy storage and solar plus storage. I could give some of my opinions. I don't know if that's appropriate here, but there are the typical values that the HCA would develop are the thermal constraints and the voltage power quality constraints, protection issues, and then variably reliability in terms of reconfiguration ability, basically. Or sometimes anti-islanding as well. And, really just from kind of a high level, I think, we're thinking about how can we kind of integrate that into the interconnection process or allow for enough of that information to be useful to the developer so that they can craft that storage system, potentially using those controls, potentially using schedules in order to mitigate potential impacts and stay within the hosting capacity. So I think, the more granular that data is temporally, as well as, what information is given in terms of what types of constraints there are, whether it's a thermal constraint or a voltage constraint, trying to pinpoint the actual constraints so that the developer can see, what are the potential mitigations. That's going to be the most useful for us. But yeah, to be developed as part of the project. Thank you for that.
And I just stopped sharing my screen. So if we could put back up the slides, and we have that last slide with our email addresses. And thank you all so much for participating. And thank you to ESA again for hosting and for helping us to run this. This has been really great. And Radina, I don't know if you want to close this out, or Mark.
Yeah, thanks, Radina. Just want to remind folks that we do have a planning and energy storage seminar slated for December 2nd and 3rd. And thank you very much for attending. And thanks very much to the IREC team for putting together a great presentation. And I hope everybody has a happy and healthy weekend. Bye-bye.
Thank you so much, Mark and all.
Yes, thank you.